What if the universe left behind a hidden message, a cosmic blueprint, that could reveal the existence of alien life? Imagine a map so ancient, it dates back to the very birth of everything we know, a map etched in the faint glow of the cosmic microwave background, or CMB. This afterglow of the Big Bang isn't just a relic of the past. It's a treasure trove of clues about the universe's infancy and, perhaps, the key to unlocking the mystery of extraterrestrial civilizations. Could this faint whisper of light hold the secrets to life beyond Earth? As we dive into the science of the CMB, we'll explore how this cosmic fingerprint might not only tell us where we came from, but also guide us to where life might exist elsewhere in the vast expanse of space. Stay with us, because by the end of this journey, you'll see the universe in a whole new light, one that might just reveal we're not alone. Now, let's take a step back in time, way back, to the very beginning of everything. Picture this: around 13.8 billion years ago, the universe as we know it didn't exist. Instead, there was a single, unimaginably dense point of energy. In an instant, this point exploded in what we now call the Big Bang, setting the stage for the cosmos we see today. But here's the fascinating part. This explosion didn't just create space and time, it also left behind a faint, glowing signature, the cosmic microwave background, or CMB. Think of the CMB as the universe's baby photo, a snapshot of its earliest moments. When the Big Bang occurred, the universe was a seething, hot soup of particles and energy. As it expanded and cooled, protons and electrons combined to form the first atoms, releasing light in the process. This light, once blazing hot, has been stretched and cooled over billions of years into the faint microwave radiation we detect today. It's like the echo of that initial explosion, still reverberating through the cosmos. The discovery of the CMB in 1965 was a monumental moment in science. Two researchers, Arno Penzias and Robert Wilson, stumbled upon this cosmic hum while working with a radio antenna. At first, they thought it was interference, but after ruling out every possible source, even cleaning out pigeon droppings from their equipment, they realized they had found something extraordinary. This discovery not only confirmed the Big Bang theory, but also gave us a direct window into the universe's infancy. Today, the CMB is considered the oldest light in the universe, a relic from a time when the cosmos was just a few 100,000 years old. It's a treasure map of sorts, revealing tiny fluctuations in temperature that would later grow into the galaxies, stars, and planets we see today. By studying these fluctuations, scientists can piece together the story of how the universe evolved, and perhaps even uncover clues about where life might exist beyond our own corner of space. So, as we explore this ancient light, we're not just looking back in time, we're also searching for answers about our place in the cosmos. Now that we've set the stage with the origins of the cosmic microwave background, let's dive deeper into what it actually is and why it's so remarkable. Imagine the CMB as a kind of cosmic fingerprint, a faint, almost imperceptible glow that fills the entire universe. This glow is incredibly cold, with an average temperature of just 2.725 degrees above absolute zero. To put that into perspective, absolute zero is the coldest possible temperature, where all molecular motion stops. So, the CMB is essentially the universe's way of whispering to us from its earliest days. What makes the CMB so fascinating is its near-perfect uniformity. No matter where you look in the sky, the temperature of this ancient light is almost exactly the same, varying by less than 100,000th of a degree. This uniformity tells us that the early universe was incredibly smooth and evenly distributed. But here's the twist. Those tiny fluctuations in temperature, those minuscule differences, are what make the CMB so valuable. They're like the seeds of cosmic structure, the tiny ripples that would eventually grow into the galaxies, stars, and planets we see today. To understand why these fluctuations matter, think of the early universe as a vast, calm ocean. The CMB captures the moment when that ocean was just starting to ripple, setting the stage for the formation of everything we know. These ripples are the result of quantum fluctuations, tiny, random variations in energy that occurred in the first fraction of a second after the Big Bang. Over billions of years, gravity amplified these fluctuations, pulling matter together to form the first stars and galaxies. Without these tiny imperfections, the universe would have remained a featureless void. But the CMB isn't just a snapshot of the early universe. It's also a powerful tool for scientists. By mapping these temperature variations, researchers can reconstruct the conditions of the universe when it was just a few 100,000 years old. It's like having a time machine that lets us peer back to a time before stars or galaxies existed. And as we study this ancient light, we're not just learning about the past, we're also uncovering clues about the universe's future, including the mysterious forces of dark matter and dark energy that continue to shape its evolution. So, the next time you hear about the cosmic microwave background, remember, it's not just a faint glow in the sky, it's a window into the universe's infancy, a treasure trove of information that helps us piece together the story of everything. And as we continue to explore its secrets, we're not just looking back in time, we're also searching for answers about the very nature of existence itself. Now, let's take a closer look at how the cosmic microwave background acts as a cosmic time capsule, preserving the secrets of the universe's earliest moments. Think of the CMB as a snapshot frozen in time, capturing the universe when it was just a few 100,000 years old. At this point, the cosmos was a hot, dense soup of particles, but something extraordinary was about to happen: the era of recombination. During this pivotal period, the universe had cooled enough for electrons and protons to combine and form the first atoms, primarily hydrogen. This process, known as recombination, marked a turning point in cosmic history. Before this, the universe was so hot and energetic that light couldn't travel freely. It was constantly scattered by free electrons. But once atoms formed, light could finally move unimpeded, creating the first clear glow of the universe. This glow is what we now detect as the CMB. The CMB gives us a direct glimpse into this era, allowing us to study the conditions of the universe at that critical moment. By analyzing the temperature and density variations in the CMB, scientists can reconstruct how matter was distributed back then. These tiny fluctuations are like cosmic breadcrumbs, leading us to understand how the first structures in the universe began to take shape. Without these clues, we'd have no way of knowing how the universe transitioned from a smooth, uniform state to the rich, complex web of galaxies and stars we see today. But the CMB doesn't just tell us about the formation of atoms, it also reveals the seeds of cosmic structure, those slight variations in temperature and density we mentioned earlier. They're the fingerprints of quantum fluctuations from the universe's first moments. Over billions of years, gravity amplified these fluctuations, pulling matter together to form the first stars, galaxies, and eventually, planets. In a way, the CMB is the blueprint for everything that exists today. What's even more remarkable is that the CMB allows us to test our theories about the early universe with incredible precision. For example, the amount of hydrogen and helium we observe in the universe today matches the predictions made by studying the CMB. This consistency gives us confidence that our understanding of the universe's infancy is on the right track. So, when we look at the CMB, we're not just seeing a faint glow, we're peering into a time capsule that holds the story of how the universe grew from a hot, dense soup of particles into the vast, structured cosmos we inhabit today. And as we continue to decode its secrets, we're uncovering the origins of everything, from the first atoms to the galaxies that light up the night sky. Now, let's shift our focus to how scientists have mapped the cosmic microwave background, turning this faint glow into a detailed blueprint of the universe's structure. To uncover the secrets hidden within the CMB, researchers have relied on a series of groundbreaking space missions, each more advanced than the last. These satellites, COBE, WMAP, and Planck, have been our eyes in the cosmos, capturing the CMB with unprecedented precision and revealing the subtle variations that hold the key to understanding the universe's evolution. The journey began with the Cosmic Background Explorer, or COBE, launched in 1989. COBE was the first mission to detect the tiny temperature fluctuations in the CMB, confirming that the early universe wasn't perfectly smooth. These fluctuations, though incredibly small, just 1 part in 100,000, were the seeds of all cosmic structure. COBE findings were so significant that they earned the team behind it the Nobel Prize in Physics in 2006. It was a monumental step forward, but it was only the beginning. Next came the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001. WMAP took the baton from COBE and ran with it, mapping the CMB with even greater detail. Its observations allowed scientists to measure the age of the universe with remarkable accuracy, 13.7 billion years, and to determine the proportions of ordinary matter, and dark energy. WMAP data also provided crucial insights into the geometry of the universe, confirming that it is flat, a finding that has profound implications for our understanding of cosmic expansion. Then, in 2009, the Planck satellite took the stage, pushing the boundaries of CMB mapping even further. Planck's instruments were so sensitive that they could detect temperature variations as small as 1 part in a million. This level of precision allowed scientists to refine their measurements of the universe's composition and to test theories about its earliest moments, including the rapid expansion known as inflation. Planck's data also revealed subtle anomalies in the CMB, sparking new questions about the fundamental laws of physics and the possibility of other universes beyond our own. Together, these missions have transformed the CMB from a faint afterglow into a detailed map of the universe's origins. The tiny fluctuations they've uncovered are like the brushstrokes of a cosmic artist, painting the first outlines of galaxies, stars, and planets. By studying these patterns, scientists can trace the growth of cosmic structures over billions of years, from the first clumps of matter to the vast web of galaxies we see today. But the story doesn't end there. The CMB continues to be a treasure trove of information, offering clues about the nature of dark matter, dark energy, and even the possibility of life beyond our planet. As we refine our maps and deepen our understanding, we're not just uncovering the history of the universe, we're also charting the path to answering some of humanity's most profound questions. What lies beyond the observable universe? Are we alone in the cosmos? The CMB may hold the answers, and with each new discovery, we're one step closer to unraveling the mysteries of existence. Now, let's take a step beyond our universe and explore one of the most mind-bending ideas in modern cosmology, the multiverse. Could the cosmic microwave background, this ancient light from the dawn of time, hold clues to the existence of other universes? The concept of the multiverse suggests that our universe might be just one of countless others, each with its own unique set of physical laws and constants. It's a staggering idea, but one that has gained traction among scientists, and the CMB might just be the key to unlocking this cosmic mystery. When we look at the CMB, we're seeing the universe as it was just 380,000 years after the Big Bang. But what if the story doesn't end there? Some theories propose that the rapid expansion of the early universe, known as inflation, didn't just happen once. It could have occurred in multiple regions, creating a vast network of bubble universes. These bubbles might be forever out of reach, but their existence could leave subtle imprints on the CMB. For instance, if two universes collided or brushed against each other during inflation, the energy from that interaction could have left a faint mark in the CMB's temperature patterns. This is where the Planck satellite's observations come into play. While mapping the CMB with incredible precision, Planck detected strange anomalies, areas where the temperature fluctuations don't quite match what we'd expect. Some scientists speculate that these irregularities could be evidence of other universes influencing our own. Imagine the CMB as a cosmic fingerprint, and these anomalies as smudges left by neighboring universes. It's a tantalizing possibility, though one that's still hotly debated. The multiverse theory also ties into the idea of fine-tuning. Our universe seems perfectly calibrated for life, with physical constants like gravity and the speed of light set just right. If there are countless other universes, each with different constants, it's possible that ours is simply one of the rare ones where life could emerge. The CMB, with its detailed map of the early universe, could help us test this idea by revealing whether the conditions we see are unique or part of a broader cosmic landscape. Of course, the multiverse remains a speculative concept, and the evidence from the CMB is far from conclusive, but that's what makes it so exciting. The CMB isn't just a relic of our universe's past, it's a window into possibilities we're only beginning to imagine. As we continue to study this ancient light, we might find answers to questions we haven't even thought to ask yet. Could the CMB be our first glimpse into a multiverse? Only time and more research will tell. Now, let's shift our gaze from the multiverse to something even more intriguing. What if the anomalies in the cosmic microwave background aren't just cosmic quirks, but signs of something far more extraordinary? Could these strange patterns be evidence of advanced alien technology? It's a bold idea, but one that has captured the imagination of scientists and science fiction enthusiasts alike. One of the most puzzling anomalies in the CMB is something called the axis of evil. This isn't a sinister plot, but rather a mysterious alignment in the temperature fluctuations of the CMB that seems to defy our expectations. According to the standard model of cosmology, these fluctuations should be random and evenly distributed, but the axis of evil shows a peculiar alignment that some researchers believe could hint at something beyond our current understanding. Could this alignment be the result of an advanced alien civilization manipulating the fabric of the universe? Imagine for a moment that a highly advanced civilization, far beyond our own technological capabilities, had the ability to harness energy on a cosmic scale. Such a civilization might leave behind traces of their activities, much like how our own industrial activities leave marks on Earth. If they were able to manipulate space-time or energy fields, the effects could ripple across the universe, imprinting themselves on the CMB. The axis of evil, with its unusual alignment, might be one such imprint, a cosmic signature of alien engineering. Of course, this idea is highly speculative, and most scientists remain skeptical. The anomalies in the CMB could just as easily be the result of unknown natural processes or even errors in our measurements, but the possibility is tantalizing. If we were to find evidence of alien technology in the CMB, it would revolutionize our understanding of the universe and our place within it. It would mean that we're not alone, and that other civilizations have reached heights of technological achievement that we can barely imagine. As we continue to study the CMB with ever more precise instruments, we may uncover more anomalies that challenge our understanding of the cosmos. Each one could be a clue, a piece of the puzzle that brings us closer to answering one of humanity's oldest questions: are we alone in the universe? The CMB, this ancient light from the dawn of time, might just hold the key to unlocking this profound mystery. And who knows, the next anomaly we discover could be the one that changes everything. Now, let's take this idea one step further. What if the cosmic microwave background isn't just a cosmic blueprint or a potential sign of alien technology, but something even more extraordinary, a message? Could this ancient light, the echo of the universe's birth, carry encoded signals from extraterrestrial civilizations? It's a fascinating thought, and one that opens up a whole new realm of possibilities. Imagine an advanced alien civilization, one that has mastered the art of communication on a universal scale. If they wanted to send a message that could be detected across vast distances of space and time, what better medium than the CMB? This faint glow permeates the entire universe, making it the ultimate cosmic billboard. By subtly altering the patterns in the CMB, such a civilization could embed information, perhaps a greeting, a warning, or even instructions for building advanced technology. The idea isn't as far-fetched as it might sound. Scientists have long speculated about the possibility of using the CMB as a communication tool. The tiny fluctuations in temperature and density that we see in the CMB could, in theory, be manipulated to encode information. These fluctuations are like the pixels of a cosmic image, and with enough precision, they could be arranged to form a message. The challenge, of course, would be in decoding it. But if we were to discover a pattern that defies natural explanations, it could be the first clue that we're not alone. Some researchers have even proposed that the CMB could contain a kind of universal language, one that any intelligent species could understand. Mathematics, for example, is often considered a universal constant. A message encoded in mathematical patterns or prime numbers could be a way for aliens to signal their presence to other civilizations. The CMB, with its intricate and precise structure, might be the perfect canvas for such a message. Of course, this is all speculative, and there's no concrete evidence to suggest that the CMB contains alien messages. But the possibility is intriguing. If we were to find such a message, it would be one of the most profound discoveries in human history. It would mean that we're part of a larger cosmic community, and that other civilizations have reached out to us across the vast expanse of space and time. As we continue to study the CMB with ever more advanced technology, we may uncover patterns or anomalies that challenge our understanding. Each one could be a potential clue, a piece of the puzzle that brings us closer to answering one of humanity's most profound questions: are we alone? The CMB, this ancient light from the dawn of time, might just hold the key to unlocking this mystery, and who knows, the next anomaly we discover could be the one that changes everything. Now, let's shift our focus to how the cosmic microwave background could play a crucial role in our search for alien life. While the CMB is often thought of as a relic of the universe's infancy, it might also serve as a guidepost for finding regions of the cosmos where life could thrive. By studying the subtle patterns and fluctuations in the CMB, scientists can gain insights into the distribution of matter and energy across the universe, which could help pinpoint areas more likely to support life. One way the CMB aids this search is by revealing the large-scale structure of the universe. The tiny temperature variations in the CMB map out the seeds of galaxy clusters, superclusters, and cosmic voids. These structures are not random. They're the result of gravitational interactions that began in the early universe. By understanding how these structures formed, we can identify regions where galaxies are more likely to host habitable planets. For instance, areas with a higher density of galaxies might offer more opportunities for life to emerge, as they provide a greater number of potential star systems with Earth-like conditions. But the CMB doesn't just tell us where to look, it also helps us understand the conditions necessary for life to exist. The CMB's uniformity and temperature provide clues about the universe's expansion and the distribution of dark matter and dark energy. These factors influence the formation of galaxies and the stability of planetary systems. For example, regions with too much dark energy might expand too quickly, preventing the formation of stable galaxies and planets. On the other hand, areas with just the right balance of matter and energy could create the perfect environment for life to flourish. Another fascinating possibility is that the CMB could help us detect signs of advanced alien civilizations indirectly. If an alien civilization were to harness vast amounts of energy, perhaps by building megastructures like Dyson spheres, they might leave subtle imprints on the CMB. These imprints could appear as anomalies in the temperature or polarization of the CMB, hinting at the presence of intelligent life. While this idea is still speculative, it highlights how the CMB could serve as a tool for both finding habitable regions and detecting the fingerprints of alien technology. Of course, the search for alien life is a complex puzzle, and the CMB is just one piece of it. But by combining insights from the CMB with data from telescopes and other instruments, we can narrow down our search and focus on the most promising areas of the universe. The CMB, in this sense, acts like a cosmic roadmap, guiding us toward the regions where life might be waiting to be discovered. As we continue to explore the universe, the CMB remains a powerful tool in our quest to answer one of humanity's most profound questions: are we alone? By decoding the secrets of this ancient light, we might just find the clues we need to uncover the existence of life beyond Earth. And who knows, the next breakthrough in our understanding of the CMB could bring us one step closer to making contact with another civilization. Now, let's take a closer look at how the cosmic microwave background sheds light on two of the universe's greatest mysteries: dark matter and dark energy. These invisible forces shape the cosmos in profound ways, and understanding them through the CMB could hold the key to uncovering the conditions necessary for alien life to exist. The CMB's temperature fluctuations are like a cosmic fingerprint, revealing the distribution of matter and energy in the early universe. But here's the fascinating part: most of the matter in the universe isn't the kind we can see. It's dark matter, a mysterious substance that doesn't emit light or energy, but exerts a gravitational pull on everything around it. By analyzing the patterns in the CMB, scientists can map out where dark matter is concentrated. These dense regions act as gravitational anchors, pulling in ordinary matter and forming the seeds of galaxies and galaxy clusters. Without dark matter, the universe as we know it, and the potential for life might not exist. But dark matter isn't the only invisible force at play. Dark energy, an even more enigmatic phenomenon, is causing the universe to expand at an accelerating rate. The CMB provides critical clues about how dark energy has influenced the cosmos over billions of years. For instance, the CMB's uniformity and slight temperature variations tell us how the universe has expanded since its birth. If dark energy were too weak, the universe might have collapsed back on itself long ago. If it were too strong, galaxies and stars might never have formed. The delicate balance between dark matter and dark energy, as revealed by the CMB, suggests that the universe is finely tuned for the emergence of structure and potentially life. So, how does this connect to alien life? The distribution of dark matter and the influence of dark energy determine where and how galaxies form. Galaxies are the cradles of stars and planets, and without them, life as we know it wouldn't have a place to take root. By studying the CMB, we can identify regions of the universe where dark matter has created the ideal conditions for galaxies to thrive. These regions might be more likely to host habitable planets, offering a greater chance for life to emerge and evolve. Moreover, the interplay between dark matter and dark energy could influence the long-term stability of planetary systems. In regions where dark energy dominates, the rapid expansion of space might prevent the formation of stable galaxies and planets. But in areas where dark matter's gravitational pull balances dark energy's push, the conditions could be just right for life to flourish. The CMB, in this sense, acts as a cosmic detective, helping us piece together the story of how the universe's invisible forces shape the potential for life. As we continue to decode the secrets of the CMB, we gain a deeper understanding of how dark matter and dark energy have shaped the universe, and how they might influence the existence of life beyond Earth. These invisible forces, once thought to be mere curiosities, could hold the key to answering one of humanity's most profound questions: are we alone? And as we explore the CMB's clues, we might just find that the universe has been leaving us breadcrumbs all along, guiding us toward the discovery of life in the cosmos. Now, let's shift our focus to one of the most intriguing questions the cosmic microwave background raises. Is the universe finely tuned for life? The CMB doesn't just tell us about the early universe, it also reveals the precise values of fundamental constants that make life possible. These constants, like the strength of gravity, the speed of light, and the mass of particles, are so perfectly balanced that even the slightest change would render the universe lifeless. This delicate balance is what scientists call the fine-tuning problem, and it's a mystery that has puzzled physicists and philosophers alike. Imagine the universe as a vast, intricate machine. Every gear, every lever, every dial has to be set just right for the machine to function. If gravity were even a tiny bit stronger, stars would burn out too quickly, leaving no time for planets to form or life to evolve. If the speed of light were slightly slower, the universe might never have cooled enough for atoms to form. These constants, imprinted in the CMB, are like the settings on a cosmic control panel, and they're set to values that allow galaxies, stars, and planets to exist. But here's the kicker: the odds of these constants aligning by chance are astronomically low. So, what does this mean? Is it just a cosmic coincidence, or is there something more at play? Some scientists argue that the fine-tuning of the universe points to the existence of a multiverse, a vast collection of universes, each with its own set of physical constants. In this scenario, our universe is just one of countless others, and we happen to live in the one where the constants are right for life. Others suggest that the fine-tuning might be evidence of a deeper, yet to be discovered law of physics that governs these constants. And then there are those who wonder if the fine-tuning is intentional, a sign that the universe was designed with life in mind. While this idea ventures into the realm of philosophy, it's a question that the CMB forces us to confront. The CMB's role in this debate is crucial. By providing a snapshot of the early universe, it allows us to measure these constants with incredible precision. For example, the CMB reveals the exact ratio of ordinary matter to dark matter, a ratio that had to be just right for galaxies to form. It also shows us the universe's expansion rate, which had to balance perfectly with the force of gravity to create the structures we see today. These measurements aren't just numbers, they're clues to understanding why the universe is the way it is, and whether it had to be this way for life to exist. So, what does the fine-tuning problem mean for the search for alien life? If the universe's constants are finely tuned for life, it raises the possibility that life isn't a rare accident, but a natural outcome of the cosmos. It suggests that the conditions for life might be more common than we think, existing wherever the right balance of constants is found. The CMB, in this sense, isn't just a relic of the past, it's a guide to the future, pointing us toward regions of the universe where life might thrive. As we continue to unravel the mysteries of the CMB, the fine-tuning problem reminds us of how extraordinary our universe truly is. Whether it's the result of chance, a multiverse, or something beyond our current understanding, the CMB challenges us to think deeply about our place in the cosmos. And as we ponder these questions, we might just find that the universe has been whispering its secrets to us all along, hidden in the faint glow of the cosmic microwave background. Now, let's venture into a fascinating possibility. Could advanced alien civilizations be using the cosmic microwave background in ways we've only begun to imagine? The CMB, as we've seen, is a treasure trove of information about the universe's origins and structure. But for a highly advanced species, it might also serve as a cosmic tool, a universal map, a communication network, or even a source of energy. Let's explore how this ancient light could play a role in the lives of extraterrestrial beings far beyond our understanding. Imagine an alien civilization that has mastered the art of interstellar travel. For them, the CMB could act as a cosmic GPS, providing a constant reference point across the vast expanse of space. Just as ancient sailors used the stars to navigate, an advanced species might use the subtle variations in the CMB to chart their course through the galaxy. These tiny fluctuations, imprinted in the early universe, could serve as markers, guiding them to distant stars or even other galaxies. The CMB, in this sense, becomes a universal roadmap, etched into the fabric of space itself. But navigation is just the beginning. What if the CMB could also be used for communication? The universe is filled with noise, radio waves, cosmic rays, and other forms of radiation. Yet, the CMB stands out as a steady, omnipresent signal. An advanced civilization might encode messages within this background radiation, using it as a medium to transmit information across unimaginable distances. Unlike radio signals, which weaken over time, the CMB is everywhere, making it a potentially ideal way to send messages that could be detected by other intelligent beings. Could the faint whispers of the CMB already contain signals we haven't yet learned to decode? And then there's the possibility of energy harvesting. The CMB, though faint, permeates the entire universe. For a civilization with the right technology, it might be possible to tap into this energy source, converting the ancient light into power for their advanced machines. While this idea might sound like science fiction, it's worth considering that the CMB represents a vast reservoir of energy waiting to be harnessed by those who know how. If alien civilizations have reached a level of technological sophistication far beyond our own, the CMB could be a key part of their energy infrastructure. Of course, these ideas are speculative, but they highlight the profound ways the CMB might intersect with the lives of extraterrestrial beings. For us, the CMB is a window into the past, a way to understand the universe's origins. But for an advanced civilization, it could be so much more: a tool, a resource, and perhaps even a means of connection. As we continue to study the CMB, we might one day uncover clues that hint at the presence of such civilizations, hidden in the faint glow of the universe's oldest light. This cosmic connection between the CMB and alien life reminds us that the universe is full of possibilities we've yet to explore. Whether it's navigation, communication, or energy, the CMB could hold the key to understanding not just our universe, but the civilizations that might share it with us. And as we ponder these ideas, we're reminded once again of the profound mysteries that lie waiting to be discovered in the cosmic microwave background. Now, let's turn our attention to one of the most puzzling questions in science: the Fermi paradox. If the universe is so vast and filled with countless stars and planets, why haven't we found any evidence of alien life? The cosmic microwave background might hold some clues to this mystery. The CMB, as we've discussed, is a snapshot of the early universe, but it could also offer insights into why intelligent civilizations seem so elusive. One possibility is that the CMB reveals something fundamental about the conditions necessary for life to thrive. The tiny fluctuations in the CMB show us how matter was distributed in the early universe, leading to the formation of galaxies, stars, and planets. But what if these fluctuations also created regions of the cosmos that are more or less hospitable to life? Perhaps the universe isn't as evenly suited for life as we might think. The CMB could help us identify dead zones, areas where the conditions are too harsh or unstable for civilizations to develop. This might explain why, despite the vastness of space, intelligent life is rare or difficult to detect. Another angle to consider is the role of time. The CMB gives us a glimpse of the universe when it was just a few 100,000 years old. Since then, billions of years have passed, and countless civilizations could have risen and fallen without leaving a trace. The CMB reminds us that the universe is not just vast in space, but also in time. Alien civilizations might exist, but they could be separated from us by such immense stretches of time that our paths never cross. The CMB, in this sense, is a reminder of how fleeting and isolated moments of life might be in the grand timeline of the cosmos. There's also the possibility that advanced civilizations are deliberately avoiding detection. If they've mastered the use of the CMB for communication or energy, they might be operating in ways that are invisible to our current technology. The CMB could serve as a kind of cosmic camouflage, allowing them to remain hidden while still interacting with the universe on a profound level. This idea ties back to the Fermi paradox. If alien civilizations are out there, they might be using the CMB in ways we can't yet comprehend, making them effectively invisible to us. Finally, the CMB might help us refine our search for alien life. By studying the patterns and anomalies in the CMB, we could identify regions of the universe that are more likely to harbor life. This could guide our efforts in the search for extraterrestrial intelligence, helping us focus on areas where the conditions are just right. In a way, the CMB could act as a cosmic filter, narrowing down the places where we're most likely to find signs of intelligent beings. The Fermi paradox challenges us to think deeply about our place in the universe, and the CMB offers a unique lens through which to explore this mystery. Whether it's revealing the uneven distribution of life-friendly conditions, highlighting the vastness of cosmic time, or hinting at the hidden activities of advanced civilizations, the CMB reminds us that the universe is full of secrets waiting to be uncovered. As we continue to study this ancient light, we might one day find answers to the question that has puzzled us for so long: are we truly alone? Now, let's shift our gaze to an even more intriguing possibility. Could the cosmic microwave background reveal the existence of alien megastructures? Imagine civilizations so advanced that they've built colossal constructs, like Dyson spheres, designed to harness the energy of entire stars. These megastructures, if they exist, might leave subtle but detectable imprints on the CMB, offering us a glimpse into the activities of extraterrestrial engineers. A Dyson sphere, for instance, is a hypothetical structure that surrounds a star to capture its energy output. If such a megastructure were built, it would alter the way energy is distributed in its vicinity. This could create anomalies in the CMB, such as unusual temperature fluctuations or patterns that stand out from the natural background. Scientists have already begun searching for these kinds of signatures, using the CMB as a cosmic detective tool to uncover evidence of alien technology. But it's not just Dyson spheres that could leave their mark. Other megastructures, like massive space habitats or interstellar communication arrays, might also interact with the CMB in unique ways. For example, a civilization using the CMB as a medium for communication could encode messages within its subtle variations. These messages, if detected, would be like finding a cosmic postcard from an advanced alien race. The CMB, in this context, becomes more than just a relic of the early universe. It transforms into a potential archive of extraterrestrial activity. Of course, detecting these imprints is no easy task. The CMB is incredibly faint, and any signals from alien megastructures would be buried under layers of cosmic noise. But with increasingly sophisticated technology, like next-generation telescopes and advanced data analysis techniques, we're getting better at sifting through this noise. The search for alien megastructures in the CMB is a long shot, but it's one that could revolutionize our understanding of the universe and our place within it. What's fascinating is that this search ties directly into the Fermi paradox. If advanced civilizations are building megastructures, why haven't we found them yet? One possibility is that their imprints are so subtle or so rare that we've simply missed them. Another is that these civilizations are intentionally hiding their activities, using the CMB as a kind of cosmic cloak. Either way, the CMB offers a tantalizing avenue for exploration, one that could bring us closer to answering the ultimate question: are we alone? As we continue to study the CMB, we're not just looking back in time to the birth of the universe, we're also peering into the future, imagining what might be possible for civilizations far beyond our own. The search for alien megastructures in the CMB is a reminder that the universe is full of mysteries, and that even the oldest light in the cosmos might hold secrets we've yet to uncover. Now, let's take a step back and consider how the cosmic microwave background might intersect with one of the most famous tools in the search for extraterrestrial life, the Drake equation. This equation, developed by astronomer Frank Drake, is a way to estimate the number of active communicative civilizations in our galaxy. It takes into account factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. But here's where the CMB comes in. It could actually help refine some of these variables, giving us a clearer picture of where and how often intelligent life might arise. One of the key factors in the Drake equation is the number of planets that fall within the habitable zone of their stars, the so-called Goldilocks zone, where conditions are just right for liquid water to exist. The CMB, as a map of the early universe, provides clues about the distribution of matter and energy that eventually led to the formation of galaxies and stars. By studying the CMB, scientists can better understand how common certain types of stars and planetary systems are, which in turn helps us estimate how many potentially habitable planets might be out there. But the CMB's influence doesn't stop there. Another critical factor in the Drake equation is the likelihood of life developing on a habitable planet. The CMB's insights into the early universe can shed light on the conditions that might have been necessary for life to emerge. For example, the CMB reveals the precise balance of matter and energy that allowed the first atoms to form, setting the stage for the chemical processes that eventually led to life. If the universe's initial conditions had been even slightly different, life as we know it might never have arisen. This fine-tuning, as revealed by the CMB, suggests that the emergence of life might be more likely in certain regions of the universe than others. Moreover, the CMB could also inform our understanding of how long civilizations might last, another factor in the Drake equation. If advanced civilizations are capable of harnessing the energy of stars or even the CMB itself, as we've discussed earlier, they might be able to sustain themselves for incredibly long periods. This could mean that the window for detecting such civilizations is much wider than we previously thought, increasing the chances that we might one day find evidence of their existence. Of course, the Drake equation is still a work in progress, and many of its variables remain uncertain. But by incorporating data from the CMB, we can start to fill in some of these gaps, bringing us closer to a more accurate estimate of how many intelligent civilizations might be out there. The CMB, in this sense, isn't just a relic of the past. It's a tool for shaping our understanding of the future, and perhaps even our place among the stars. As we continue to explore the mysteries of the CMB, we're not just uncovering the history of the universe, we're also gaining insights that could help us answer one of humanity's most profound questions: are we alone? And with each new discovery, we move one step closer to finding out. Now, let's shift our focus to something even more mind-bending: the role of quantum fluctuations in the early universe and how they might have shaped the very fabric of life itself. These tiny, random variations in energy, imprinted in the cosmic microwave background, are like the universe's first brushstrokes, small but incredibly significant. Without them, the cosmos, as we know it, might not exist at all. Quantum fluctuations are essentially the universe's way of introducing a little chaos into the mix. In the earliest moments after the Big Bang, these fluctuations caused slight irregularities in the distribution of matter and energy. Over billions of years, these tiny ripples grew, eventually leading to the formation of galaxies, stars, and planets. But here's where it gets fascinating. These same fluctuations might have also played a crucial role in creating the conditions necessary for life to emerge. Think of it like this: the universe started with a nearly uniform soup of particles, but thanks to quantum fluctuations, some regions became slightly denser than others. These denser regions acted as seeds, pulling in more matter through gravity and eventually forming the structures we see today. Without these initial irregularities, the universe might have remained a featureless void, devoid of the complexity needed for life to arise. But the influence of quantum fluctuations doesn't stop at the formation of galaxies. They might have also set the stage for the chemical processes that make life possible. For instance, the distribution of elements like carbon, oxygen, and nitrogen, essential building blocks of life, could have been shaped by these early fluctuations. If the universe had been perfectly smooth, these elements might not have clustered in the right ways to form planets with the right conditions for life. Even more intriguing is the possibility that quantum fluctuations could have influenced the very nature of life itself. Some scientists speculate that these early variations might have created pockets of the universe where the laws of physics are slightly different, potentially leading to entirely new forms of life. Imagine a distant galaxy where the fundamental constants of nature are tweaked just enough to allow for life that's radically different from anything we've ever imagined. Of course, this is still largely speculative, but it's a reminder of just how interconnected everything in the universe truly is. The same quantum fluctuations that shaped the cosmos billions of years ago might have also set the stage for the emergence of life not just here on Earth, but potentially across the universe. And as we continue to study the CMB, we're uncovering more clues about how these tiny ripples in space-time might have influenced the grand tapestry of existence. So, the next time you look up at the night sky, remember this: the stars, the planets, and even the possibility of alien life might all trace back to those first, fleeting moments of quantum chaos. It's a humbling thought, and one that reminds us just how deeply we're connected to the universe's earliest beginnings. Now, let's take a closer look at how the cosmic microwave background might help us pinpoint the Goldilocks zones of the universe, those regions that are just right for life to emerge and thrive. Just as Earth sits in a habitable zone around the Sun, where conditions are perfect for liquid water and life as we know it, the universe itself may have its own cosmic sweet spots, and the CMB could be the key to finding them. The CMB provides us with a detailed map of the early universe, showing tiny variations in temperature and density that eventually led to the formation of galaxies and clusters of galaxies. These fluctuations aren't just random, they're clues about where matter was more concentrated in the early universe, and where it might have created the right conditions for life to develop. By studying these patterns, scientists can identify regions where the universe's structure is most conducive to the formation of planets, stars, and even the complex chemistry needed for life. For example, areas with slightly higher densities in the early universe would have attracted more matter over time, leading to the formation of galaxies with stable star systems. Within these galaxies, planets could form in the habitable zones of their stars, where temperatures allow for liquid water, a key ingredient for life as we understand it. The CMB helps us trace these regions back to their origins, giving us a better understanding of where life might have the best chance to emerge. But the Goldilocks zone isn't just about location, it's also about timing. The universe has been expanding and evolving for billions of years, and the conditions for life might only exist during specific cosmic eras. The CMB allows us to peer back in time, helping us identify when and where the universe was most hospitable for life. For instance, in the early universe, radiation levels were too high for complex molecules to form, but as the universe cooled, the conditions became just right for the chemistry of life to begin. What's even more fascinating is the possibility that the CMB could reveal regions of the universe where the fundamental constants of nature are perfectly tuned for life. Some scientists speculate that these constants, like the strength of gravity or the charge of an electron, might vary slightly across the cosmos. If that's the case, the CMB could help us find areas where these constants are ideal for the emergence of life, even if it's radically different from life on Earth. So, while we often think of the Goldilocks zone as a small, cozy region around a star, the CMB invites us to think bigger. It suggests that the entire universe might have its own Goldilocks zones, places where the conditions are just right for life to take root and flourish. And as we continue to study the CMB, we're not just mapping the universe's past, we're also uncovering the cosmic recipe for life itself. This brings us to an even bigger question. If the universe has these Goldilocks zones, could alien civilizations be thriving in them right now? And if so, how might they be using the CMB to navigate or even communicate across the vastness of space? These are the kinds of questions that keep scientists and all of us looking up at the stars, wondering what secrets the universe still holds. Now, let's shift our perspective and imagine how an advanced alien civilization might view the cosmic microwave background. If life exists elsewhere in the universe, it's likely that other intelligent beings would also study the CMB just as we do. But what might they see, and what could they learn about the cosmos, and perhaps even about us? For an alien civilization, the CMB would serve as a universal map, a snapshot of the early universe that's accessible to anyone with the right technology. Just as we use it to trace the origins of galaxies and the distribution of matter, they might analyze its patterns to understand the structure of the universe on a grand scale. But their interpretation could be vastly different from ours, shaped by their unique perspective and technological capabilities. Imagine a civilization far more advanced than ours, with tools that allow them to detect even the subtlest variations in the CMB. They might uncover details about the universe's expansion rate, the distribution of dark matter, or even the presence of other universes beyond our own. For them, the CMB could be more than just a relic of the past. It might be a living, dynamic tool for exploring the cosmos. But here's where it gets even more intriguing. If these alien observers are studying the CMB, they might also be looking for signs of other civilizations like us, just as we search for anomalies or patterns that could hint at alien technology. They might be doing the same. The CMB could act as a cosmic message board, where civilizations leave subtle imprints of their existence. For example, if an advanced civilization had harnessed the energy of stars or built megastructures, these activities might leave faint traces in the CMB that could be detected across vast distances. And what if these alien observers are not just passive students of the CMB, but active participants? Some scientists have speculated that advanced civilizations might use the CMB as a communication medium, encoding messages in its fluctuations or using it to navigate the universe. If that's the case, the CMB could be a kind of cosmic internet, connecting civilizations across the expanse of space and time. Of course, this raises a fascinating question. If aliens are studying the CMB, what might they think of us? Would they see Earth as a tiny, insignificant speck in the grand scheme of the universe? Or would they recognize the signs of a young, curious civilization reaching out to understand its place in the cosmos? The CMB might not just be a window into the universe's past, it could also be a mirror, reflecting our own journey of discovery. As we continue to explore the CMB, we're not just uncovering the secrets of the universe, we're also opening a dialogue with the unknown. Whether or not we ever make contact with alien civilizations, the CMB reminds us that we're part of a much larger story, one that's still being written. And who knows, perhaps somewhere out there, another civilization is looking at the same ancient light, wondering if they're alone in the universe, just like we are. Now, let's take a step into one of the most profound aspects of the cosmic microwave background, its connection to the arrow of time. The CMB isn't just a map of the universe's early moments, it's also a key to understanding how time itself flows. But what does that mean, and how does it shape the story of life in the cosmos? The arrow of time refers to the one-way direction in which time moves, from the past to the future. It's why we remember yesterday, but not tomorrow, and why a broken glass doesn't spontaneously reassemble itself. The CMB plays a crucial role in defining this direction. As the oldest light in the universe, it marks the beginning of time as we know it, setting the stage for everything that followed. The uniformity of the CMB represents a state of low entropy, or high order, in the early universe. Over billions of years, entropy has increased, driving the universe toward greater complexity and disorder. This increase in entropy is what gives time its direction. But here's where it gets even more fascinating. The arrow of time isn't just a cosmic curiosity, it's essential for the emergence of life. Life as we know it depends on processes that are irreversible, like the flow of energy and the progression of chemical reactions. Without the arrow of time, these processes wouldn't exist, and neither would we. The CMB, by defining the starting point of time, essentially set the stage for the evolution of life in the universe. Now, imagine how this might play out on a cosmic scale. If the arrow of time is universal, then every civilization, no matter how distant, would experience time in the same way. They too would see the universe evolving from a state of low entropy to higher entropy, just as we do. This shared experience of time could be a unifying thread across the cosmos, connecting all life forms in a common narrative of growth and change. But what if the arrow of time isn't the same everywhere? Some theories suggest that in other regions of the universe, or even in other universes, time might flow differently. Could there be places where entropy decreases and time runs backward? While this idea remains speculative, it raises intriguing questions about the diversity of life and the conditions necessary for its existence. If time behaves differently elsewhere, could life evolve in ways we can't even imagine? The CMB also offers clues about the ultimate fate of time. As the universe continues to expand, entropy will keep increasing, leading to a state known as heat death, where energy is evenly distributed and no more work can be done. This might seem like a bleak future, but it's also a reminder of the preciousness of the time we have. The arrow of time, as defined by the CMB, gives us a finite window to explore, create, and connect, not just with each other, but with the universe itself. As we ponder the CMB's role in shaping time, we're reminded that our existence is deeply intertwined with the cosmos. The arrow of time isn't just a scientific concept, it's a story of how the universe unfolds and how life emerges within it. And as we continue to study the CMB, we're not just uncovering the secrets of time, we're also discovering our place in its grand, irreversible flow. Now, let's shift our gaze to how the cosmic microwave background might play a role in one of humanity's most ambitious quests, the search for extraterrestrial intelligence. For decades, SETI researchers have scanned the skies, listening for signals that could indicate the presence of alien civilizations. But what if the CMB, this ancient echo of the universe's birth, could offer a new way to refine that search? the CMB is more than just a snapshot of the early universe. It's a backdrop against which all cosmic signals are measured. Its uniformity and predictability make it an ideal reference point for detecting anomalies that could hint at intelligent life. Imagine the CMB as a vast, cosmic canvas. Any unusual patterns or deviations in this canvas could potentially be signs of advanced alien technology or communication. For instance, if an alien civilization were to manipulate the CMB in some way, perhaps by encoding messages within its fluctuations, SETI researchers might be able to detect these subtle changes. One intriguing possibility is that advanced civilizations could use the CMB as a universal communication medium. Because the CMB permeates the entire universe, it could serve as a kind of cosmic internet, allowing civilizations separated by vast distances to exchange information. If aliens were to embed signals within the CMB's faint whispers, we might one day decode these messages, unlocking a new era of interstellar communication. But the CMB's role in SETI goes beyond just communication. It could also help us identify regions of the universe where life is more likely to exist. By studying the CMB's temperature fluctuations, scientists can map the distribution of matter in the early universe, revealing areas where galaxies and stars formed more densely. These regions, rich in resources and energy, might be prime locations for advanced civilizations to thrive. By focusing SETI efforts on these areas, we could increase our chances of detecting alien signals. Moreover, the CMB might hold clues about the technological capabilities of extraterrestrial civilizations. For example, if a civilization had harnessed the energy of entire galaxies, their activities could leave detectable imprints on the CMB. These imprints, though faint, might reveal the presence of megastructures or other feats of engineering that defy our current understanding of physics. Of course, searching for alien signals within the CMB is no easy task. The CMB is incredibly faint, and any potential signals would be buried under layers of cosmic noise. But as our technology advances, so too does our ability to sift through this noise and uncover hidden patterns. Future telescopes and detectors, designed with the CMB in mind, could revolutionize the way we search for extraterrestrial intelligence. As we explore the CMB's potential in the search for alien life, we're reminded of the boundless possibilities that lie within the cosmos. The CMB isn't just a relic of the past, it's a tool for the future, a key that could unlock the secrets of intelligent life beyond our planet. And as we continue to listen to the whispers of the universe, we might just find that we're not alone after all. Now, let's take a step back and consider how the cosmic microwave background might have played a role in the very origins of life itself. The CMB isn't just a relic of the universe's birth, it's also a window into the conditions that made life possible. To understand this, we need to look at how the early universe set the stage for the chemical processes that eventually led to the emergence of life on Earth, and potentially elsewhere in the cosmos. When the universe was just a few 100,000 years old, the CMB was emitted during the era of recombination, when the first atoms formed. This period marked the beginning of a cosmic chemistry lab, where simple elements like hydrogen and helium began to interact under the influence of gravity and radiation. Over billions of years, these elements clumped together to form stars, galaxies, and eventually, the complex molecules necessary for life. One fascinating theory suggests that the CMB's faint radiation may have influenced the formation of these molecules. The CMB's uniform temperature provided a stable background for chemical reactions to occur, allowing atoms to bond and form more complex structures. Without this stable environment, the delicate processes that led to the creation of amino acids and other building blocks of life might not have been possible. But the CMB's role doesn't stop there. Some scientists believe that the tiny fluctuations in the CMB's temperature, those same fluctuations that seeded the formation of galaxies, could have also influenced the distribution of matter in ways that favored the emergence of life. Regions of the universe with slightly higher densities might have had more resources for star formation, leading to planets with the right conditions for life to thrive. In this way, the CMB might have indirectly shaped the cosmic landscape, creating pockets of habitability scattered across the universe. Another intriguing idea is that the CMB's radiation could have acted as a kind of cosmic catalyst, providing the energy needed to kickstart chemical reactions on early planets. On Earth, for example, the energy from the sun and other sources played a crucial role in driving the chemical processes that led to life. But in the early universe, the CMB's radiation might have served a similar purpose, providing a universal energy source that could have jump-started life on countless worlds. Of course, these theories are still speculative, and much remains to be discovered about the exact role the CMB played in the origins of life. But what's clear is that the CMB is more than just a snapshot of the early universe. It's a key piece of the puzzle in understanding how life emerged in the cosmos. By studying the CMB, we're not just looking back in time, we're also uncovering clues about the conditions that made life possible, both here on Earth and potentially on distant planets. As we continue to explore the mysteries of the CMB, we're reminded of the profound interconnectedness of the universe. From the first atoms to the emergence of life, the CMB has been a silent witness to the unfolding story of the cosmos. And as we delve deeper into its secrets, we might just find that the origins of life are written in the faint whispers of this ancient light. As we turn our gaze toward the future, the cosmic microwave background holds incredible promise for shaping the next era of space exploration. Imagine this: the CMB isn't just a relic of the past, it's a roadmap for where we might find life beyond Earth. By studying its subtle patterns and fluctuations, scientists can identify regions of the universe that are most likely to harbor habitable worlds, guiding our search for alien life with unprecedented precision. One of the most exciting possibilities is how the CMB could help us pinpoint exoplanets with the right conditions for life. The tiny temperature variations in the CMB reveal how matter was distributed in the early universe, and these patterns influenced where galaxies and star systems formed. By mapping these cosmic blueprints, we can target star systems that are more likely to have Earth-like planets, saving time and resources in our search for extraterrestrial life. But the CMB's potential doesn't stop at distant galaxies. Closer to home, it could also inform missions within our own solar system. For example, understanding the CMB's role in the early universe might help us better predict where to look for signs of life on icy moons like Europa or Enceladus. These moons, with their subsurface oceans, could be teeming with microbial life, and the CMB's insights into the conditions that fostered life on Earth might give us clues about where to drill or explore. Moreover, the CMB could inspire new technologies for detecting life. Advanced telescopes and sensors designed to study the CMB's faint signals might be adapted to search for biosignatures, chemical traces of life, on distant planets. These tools could revolutionize our ability to detect alien life, even from light years away. Looking further ahead, the CMB might even guide humanity's efforts to colonize other worlds. By identifying regions of the universe with the most stable and life-friendly conditions, we could prioritize where to send future interstellar missions. The CMB, in this sense, becomes not just a scientific tool, but a cosmic compass pointing us toward the stars. As we continue to unlock the secrets of the CMB, one thing is clear: it's more than just a window into the past, it's a beacon for the future. Whether we're searching for life on distant exoplanets or planning humanity's next great leap into the cosmos, the CMB will be there, lighting the way. And who knows, the answers we're seeking might already be written in the faint glow of this ancient light, waiting for us to discover them, as we venture deeper into the mysteries of the cosmic microwave background. It's important to pause and consider the ethical implications of what we might discover. The search for alien life is thrilling, but it also raises profound questions about how humanity should approach such a monumental revelation. What responsibilities do we have if we find evidence of extraterrestrial intelligence? And what risks might come with making contact? One of the most pressing ethical concerns is the potential impact of first contact. If we detect signs of an advanced alien civilization, how should we respond? Sending a message could open the door to communication, but it might also expose humanity to unknown dangers. History has shown us that encounters between vastly different civilizations rarely end well for the less advanced one. Could we be risking our own safety by reaching out? On the other hand, choosing not to engage could mean missing out on an opportunity to learn from a civilization far more advanced than our own. The knowledge and technology they might share could revolutionize our understanding of the universe and solve some of humanity's greatest challenges. But this raises another ethical dilemma. Should we even attempt to influence or interfere with another civilization's development? The prime directive from science fiction comes to mind. Should we adopt a similar principle in reality? There's also the question of how we handle the discovery of microbial life. If we find evidence of simple organisms on a distant exoplanet or even within our own solar system, how should we proceed? Should we prioritize preserving these ecosystems, or would it be acceptable to study them in ways that might alter or destroy them? The ethical considerations here are similar to those we face when exploring Earth's most fragile environments, but on a cosmic scale. Moreover, the very act of searching for alien life through the CMB raises questions about humanity's role in the universe. Are we prepared to accept that we might not be alone? And if we are not, how will that knowledge reshape our sense of identity and purpose? The discovery of extraterrestrial life could challenge long-held beliefs and philosophies, forcing us to rethink our place in the cosmos. Finally, there's the responsibility of sharing this knowledge with the public. If we discover evidence of alien life, how transparent should we be about it? Releasing such information could inspire wonder and unity, but it might also cause fear or panic. Striking the right balance between openness and caution will be crucial. As we continue to explore the cosmic microwave background and its potential to reveal alien life, these ethical questions remind us that science is not just about discovery, it's about responsibility. The choices we make today could shape humanity's future for generations to come. And as we stand on the brink of potentially groundbreaking discoveries, one thing is certain: the answers we seek will challenge not just our understanding of the universe, but also our understanding of ourselves. Now, as we turn our gaze toward the ultimate question, are we alone? The cosmic microwave background offers a unique lens through which to explore this age-old mystery. This faint glow, the echo of the universe's birth, holds more than just the secrets of our cosmic origins. It may also hold clues to one of humanity's most profound inquiries. Is life a rare, fleeting phenomenon, or is it woven into the very fabric of the cosmos? The CMB, as a snapshot of the early universe, provides us with a map of the conditions that allowed galaxies, stars, and planets to form. These same conditions, as we've come to understand, are also the building blocks for life as we know it. The delicate balance of temperature, density, and energy fluctuations imprinted in the CMB suggests that the universe was, in a sense, fine-tuned for complexity. But does this fine-tuning extend to the emergence of life itself? Could the same processes that seeded galaxies also have seeded life across the cosmos? One of the most compelling aspects of the CMB is its universality. It's a signal that permeates every corner of the observable universe, a shared experience for any civilization advanced enough to detect it. If alien civilizations exist, they too would have access to this cosmic blueprint. They might even be asking the same questions we are. Is this universe teeming with life, or are we an isolated anomaly? The CMB, in this sense, becomes a common thread connecting all potential observers, a cosmic conversation starter that transcends time and space. But the CMB doesn't just connect us to alien civilizations, it also connects us to our own origins. By studying its patterns, we're essentially looking back in time to the moment when the universe became transparent, when the first atoms formed, and when the stage was set for everything that followed. This journey into the past isn't just about understanding the universe, it's about understanding ourselves. If life is a natural outcome of the universe's evolution, as some theories suggest, then the CMB might be the key to unlocking our own story. Yet, the question remains, if life is so deeply intertwined with the universe's structure, why haven't we found evidence of it beyond Earth? The Fermi paradox looms large here, challenging us to reconcile the apparent silence of the cosmos with the vastness of its possibilities. The CMB, with its subtle hints and anomalies, might hold the answer. Perhaps the conditions for life are rarer than we think, or perhaps we're simply not looking in the right way. The CMB reminds us that the universe is full of surprises, and the answers we seek may be hidden in the most unexpected places. As we continue to probe the CMB, we're not just searching for alien life, we're searching for meaning. The discovery of extraterrestrial intelligence, or even the confirmation of microbial life elsewhere, would fundamentally alter our understanding of existence. It would force us to confront the possibility that we are not the center of the universe, but rather one thread in a vast cosmic tapestry. The CMB, as a bridge between the past and the present, between the known and the unknown, brings us closer to answering this ultimate question. So, as we stand on the precipice of discovery, gazing into the depths of the cosmic microwave background, we're reminded that the search for alien life is more than a scientific endeavor. It's a journey of self-discovery. The answers we find may not only reveal whether we're alone in the universe, but also help us understand what it means to be human in a cosmos that is both vast and mysterious. And in that search, the CMB remains our most powerful guide, a beacon of light illuminating the path toward the truth. As we bring our exploration of the cosmic microwave background to a close, let's take a moment to reflect on what we've uncovered. The CMB is more than just a relic of the universe's birth. It's a cosmic map, a time capsule, and perhaps even a message waiting to be decoded. From its role in shaping galaxies and stars to its potential as a universal signal connecting civilizations across the cosmos, the CMB offers us a glimpse into the profound interconnectedness of all things. It challenges us to consider whether life is a rare accident or an inevitable outcome of the universe's design. And as we grapple with the Fermi paradox and the silence of the cosmos, the CMB reminds us that the answers we seek may be hidden in the subtlest of cosmic whispers. But the journey doesn't end here. The CMB invites us to keep exploring, to keep questioning, and to keep pushing the boundaries of what we know. Whether you're a seasoned space enthusiast or someone just beginning to ponder the mysteries of the universe, the CMB is a reminder that there's always more to discover. So, as we look to the stars and wonder about the possibility of alien life, let's also look within and ask ourselves what it means to be part of this vast, intricate cosmos. If you've enjoyed this journey through the cosmic microwave background and its connection to the search for alien life, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the mysteries of the universe. And as always, stay curious because the cosmos is full of secrets waiting to be uncovered. Until next time, keep looking up.